Radioactive waste from nuclear power plants will pose a threat to life on Earth for thousands of generations. So the copper canisters designed for its final disposal in Sweden need to remain stable for at least 100,000 years. Our own detailed studies, however, show that they might corrode in less than a century. Isn't it then critical to investigate more? Early in my scientific career, some friends jokingly asked me how I can spend so much time on rust as if it was something meaningless. And also later, when working in the field, I quite often met that attitude. Corrosion really was not fancy enough. Normally we don't think about corrosion, but it really influences our daily life in so many ways. We have cars that corrode, we have water pipes that leak, and corrosion of electronics influences industrial processes and security systems. Estimates say that cost for corrosion and corrosion protection is something around 2,000 euros per person and year, which is quite a lot. There are many examples of disasters caused by corrosion. Big bridges have collapsed. Oil pipelines have ruptured, a tanker ship breaking in half, and we have a commercial airplane that lost part of its fuselage while flying on very high altitude. And we have the biggest industrial disaster ever in Bhopal, India, when toxic gas leaked out and 500,000 people were exposed to toxic gas. Corrosion is the gradual breakdown of a metal. It can be explained by a cycle. In the beginning, the metal is found as a mineral in nature, and in order to extract the metal out of the mineral, we need to apply a lot of energy. And when we apply the energy, the metal comes into its metallic state, which is a much more unstable state. And when it's exposed to an environment, it starts to corrode. And then it forms corrosion products, which are very similar to the mineral from which the metal was extracted. And the cycle is closed. So corrosion is basically the tendency of the metal to go back to its most stable state. Many people use rusting as a synonym for corrosion, but that's not correct. Rusting is a special case of corrosion, namely that of iron and its alloys. Corrosion became a problem as soon as humans started to produce the first metals, some 10,000 years ago, and it affects all metals. Thus, in our technological society, we live under constant potential threat of corrosion failure. However, we are hardly aware of it, probably because most metal applications and objects are correctly designed and dimensioned, so corrosion is not visible at all. We have learned to protect boat hulls and propellers, or how to design stainless steel sinks that will hold for a lifetime. But for very long, we had a very limited understanding of the fundamental physical and chemical processes governing corrosion. However, it's important to understand the fundamentals behind different forms of corrosion in order to protect the metal from that form of corrosion. In the same way as when we want to protect or cure a human from a certain disease, we need to know how that disease acts and occurs. However, corrosion is generally not regarded as a strong academic field. My own university studies at KTH were in engineering physics, and there we learned nothing about corrosion at all. So when I finished my master's studies, I didn't know more about corrosion than any other average person. There have been a few exceptions in universities where corrosion really has had a strong position. And today, there are some universities in China where corrosion really is very, very strong. When I started my academic career and tried to seek for fundings to understand the fundamentals of corrosion, my applications were quite often rejected because they were regarded as too applied, simply because I used the word corrosion. And this was, of course, quite frustrating. So I had to tweak the terminology in order to increase my chances to receive fundings. And of course, that didn't feel right at all. I think that attitude towards corrosion science caused a fatal gap in our fundamental knowledge of understanding what corrosion is all about. Corrosion processes are very complicated, and in order to understand them, you really need to analyze what happens on the metal surface. And the strange thing is that while the naked eye sees the metal surface, to analyze what happens on the surface, it's extremely difficult.
Atmospheric corrosion is difficult to study since the process is very complex, as the metal surface consists of several different layers, some of these layers only being a few molecules thick. To be able to study these atmospheric corrosion processes, we need highly advanced instruments. And in addition, a corrosion process commonly does not occur evenly over a surface. So to be able to explain at the nanoscale why a corrosion process, for example, occurs at a specific point, or why some corrosion products are formed in one area and others in another area, we need instruments with a very good lateral resolution.
I entered the corrosion field through doctoral studies at KTH. In these doctoral studies, I had the chance to learn a new and quite groundbreaking technique to study surfaces. And with this technique, we explored passive films on iron and chromium, two important components in stainless steel. A passive film is an invisible and ultra-thin film of corrosion products that protects the metal from further corrosion. So by using this technique, we were able to explore details in the passive film that never had been studied before. To use this technique was quite cool and exciting because it meant the start also of a new research field, surface physics, that I felt part of. Later on, when I had finished my PhD studies, I went to the industry to present the results, and I was shocked to realize that they were not at all aware of why their products were resistant against corrosion. And this was really like an eye-opener to me. My mission from then on was to fill the gap in fundamental knowledge of the basic mechanisms of corrosion. After my doctoral studies, I had a chance to go to a very prominent laboratory at the University of California in Berkeley, where they very successfully used a variation of different surface-sensitive techniques to explore industrially important questions in catalysis, in corrosion, and in other fields. And when returning home, I thought this might be a game changer, because if I could use the same type of analytical techniques to explore important forms of corrosion, then I really could make an important step to understand the mechanisms better. But I realized that I cannot work in all kinds of corrosion. I need to specialize somewhere. And after some considerations, I choose atmospheric corrosion, which is the corrosion when the metal is exposed to the atmosphere, because it's the most costly form of corrosion, and also the most complex one to understand. So I felt this was a real challenge. Atmospheric corrosion is so complex that we cannot use the real atmosphere out there. We have to simplify it into less components. We have the metal, we have the oxide covering the metal, we have an aqueous film on top of the oxide, and then we have the atmosphere. We need different analytical techniques to characterize each of these layers, and the way to find these techniques is to collaborate with people from other fields, mainly from physics and chemistry, and adopt them to our special questions.
We use different techniques that can probe these different layers and interfaces. And by combining all this information, we can obtain more detailed information about the corrosion process. Some of the instruments, they are possible to combine in the same experiments at the same time. So in real time, we can obtain different types of information. One example is that we combine an ultra-sensitive balance that can measure the mass of the corrosion products formed in the beginning of the corrosion process, with another instrument that enabled us to determine how an organic film consisting of just one molecular layer was breaking down during the corrosion process.
What is necessary for the future to vitalize corrosion in general is to regard corrosion as an interdisciplinary arena where we collaborate with people in surface physics, for instance, to import these techniques, or atmospheric chemistry to understand how the chemistry of the atmosphere influences the metal, or industrial ecology to understand what footprints corrosion can make for our health or our environment. Crossing these borders makes corrosion science really a fascinating field to study in, even after 50 years. The most important findings in my scientific career is that we have been able to make a very detailed analysis of the initiation of atmospheric corrosion. When the metal is exposed to the atmosphere, different components enter into the aqueous water film. There they transform into other chemical substituents, and then they interact with the oxide surface on the metal, dissolve the oxide, and in this way the metal corrodes and forms corrosion products. To understand this is very important if we want to protect the metal against atmospheric corrosion. But it also meant very much for the corrosion community. It gave an echo because this was a very detailed way of understanding and explaining atmospheric corrosion. And in fact, it resulted in several of the International Corrosion Research Awards. And I must say I cannot enough express my gratitude to all the co-workers of the group who have contributed to this. Our collaboration with industry has really been a cornerstone in my scientific career. The industry saw quite early the potential of using these results for the long-term thinking, for the strategies to find new products. The industry was not able to produce that in-house. So instead, they let us and other groups like us work on these subjects, and were also financing this type of research from very early stages. And for us, this was also quite beneficial because we could, through our collaboration with industry, see and learn how the industry works and thinks, and that helped us design our experiments as well. So in many ways, it was a privilege to work in the sweet spot between industrial needs and scientific challenges. Many people say that governmental support is more sustainable because you can trust the government, while industrial support you can't trust. My experience is absolutely the opposite. While government support has been much more trendy, always focused on certain topics like nanotechnology or biotechnology. The industry has been pragmatic and always seeking to finance projects where they need to answer questions. But studying corrosion is not only about optimizing profits for the industry. There are many other fields that benefit from a deeper understanding of the corrosion phenomena. We can make beautiful works of art, such as this tapestry, which includes pieces from old copper roofs. Another area that benefits from knowledge in corrosion science is our cultural heritage. One example is the famous Vasa ship, where some 4,000 bolts who had corroded and which hold together the ship were replaced by new bolts made of stainless steel and produced by Sandvik. And hopefully the ship will now last for 150 years or more. A greater knowledge in corrosion is also beneficial for our efforts to reduce carbon dioxide emission, because we can prolong the lifetime of metals and in this way reduce their production. Corrosion can also affect our environment and our health. When the metal is corroding, it releases metal ions, and these metal ions can be very harmful depending on if the metal is in an ionic form or if it is in a more stable form. And this type of work has been very much going on in our research group and has been taken up by REACH, which is a regulation adopted by the European Union.
REACH is the regulatory framework for chemicals in Europe in order to ensure safe use and production of chemicals in different forms. It's essential because the companies have to show that their products are safe and ensure that no hazardous elements or chemicals are dispersed to the environment or can cause effects on human health. My team has been working on REACH-related aspects for more than 20 years. We have been working on metals and alloys used in different applications and different chemical settings in order to understand their physico-chemical characteristics, how those change with time, the transformation in dissolution properties, and the environmental fate of metals.
And of course, I'm very proud that our research, headed by my co-worker Inger Odenvall, has made such a strong impact. Looking back at those 50 years in which I've been active, I've seen a tremendous transformation of the corrosion field, from a fairly applied to a notably fundamental discipline, something that has also had clear consequences on the industry. In the beginning, the stainless steel producers could not even understand why their products really were stainless. And today they develop stainless steels which can withstand the harshest environment. And I'm very glad and pleased to have been part of this evolution and to have left a legacy in the form of a very active and successful research group. Also to have graduated so many doctoral students, postdocs all around the world, and to have left a book, Atmospheric Corrosion, which is now the standard book in the field, which has been cited in more than 100 countries. As I approach the end of my career, I recall a discussion I had with my father, a well-known pianist, Hans Leygraf, when I was 14. And I asked him for a career advice. And he said, "The only thing I can tell you, don't become a pianist. It's too exhausting. And whatever else you do will be just fine."